Welcome, I hear people arriving in the Zoom world. Welcome to you. We're just getting the broadcast set up. Welcome. And it looks like it works. Great. Right, things are working technology-wise. Let's get our class looking good to share with everybody out there in the Zoom world. Why is that there? Come on, the computer. You can do it. Let's share a screen. Yeah. Let's turn on a chat window. Yeah. Let's make the screen about the size. Everything fits on the place. Welcome, Drew. Welcome, Finn. Welcome, Mai. Nerys, welcome to you. We are here in the Zoom world. Welcome, Peter. Welcome.
Oh, good. I mean, that's so sweet.
My brain is a little busted this morning. Do we remember where we left off last class? And by we, I mean me. I'm going to open up our schedule to get my brain working. I think I do remember where we left off, but I want to double check. I'm heading to course materials, schedule. I'm going to make it bigger so I can read it. Welcome, welcome. I hear the bell a-ringing. Welcome to people. I'm even going to crank up the speakers in here another level. So if you want to use your mic, I'll hear you. I know what happened last class. We did not talk about this sampling distribution because we did normal distribution, catch up and finishing, and we got that lab done as planned. But this sampling distribution discussion's got to shift to today. Oh, wait. Well, so that's where we're going to start. With the second section of chapter 4. That's the plan to start there. And the dream for today, our dream would be to talk all the way through that second section and then use whatever time we have to begin our discussion of that fourth section of chapter 4. And then, we should be able to get back on track, catch up on the binomial distribution at the end of today and on Monday. And then the fifth section, that's kind of a short one. So it shouldn't be, so we should be able to be all caught up next Monday with our little hiccup in our timing. So let me make sure I'm signed into my PCC account so I can make little edits to things as we go today as needed. Of course, I always want to hear questions. That would be the best way to start class. No thanks, or continue, sure, whatever, no thanks. Okay, now let me just double check that I can refresh this. And yeah, now I can edit this. I'm going to just quickly edit that schedule so I can see it next class too, where we are. This one's going to slide down just to start that discussion next class, and as planned. Till today, we're doing that discussion, and we really did normal distribution on 2 days. Okay, now the schedule looks like real life more. And what's your question, Maria?
The 4.1 is for exercise 4.9C.
4.9, part C.
Yeah.
Okay, let's go look at that, and that'll be a great way to kick off class. I'm gonna head into I think the online textbook version, because that's the easiest one to reach via these links right here. And I got a nice big screen so I can get it big on my screen. Hey, online text, chapter 4, section 1, exercise number 9. If you're in the first section, they're numbered the same in both versions, no problem. 4, 9. all the way down here. 49C. Oh, this one's complicated. There's a little complicated trick here. So if you haven't worked on section 4, chapter 1 homework yet, I strongly recommend checking out this discussion because there's a little annoying fact here in this problem number 9 that I'll show you. I'm going to copy the problem and put it in our class notes for discussions purposes. And I'm going to end up making a little drawing because I've talked about this with many smart people before. And there's some confusion here that is real because you don't quite have all the information you need unless you think deeply upon it, more deeply than most people are going to take the time to, in the haze of life, and definitely more deeply than you're usually asked to think about these problems on your homework. So here we go. I'm heading to. Yeah, it gets a little weird in there. Let's look at this. Class notes. Let me get down to the bottom of this thing. All the way down here. It is Wednesday, February 26th. It is a 4.1 homework question. The question's called LA weather. Looks like that. Okay. The average daily high temperature in June in Los Angeles, California is 77 degrees Fahrenheit. That sounds nice. With a standard deviation of 5 degrees Fahrenheit. That's not a lot of variation. It would be weird if the temperature were lower than, say, 62 degrees one day in June there, because of, 3 standard deviations being a lot below. And it's not going to go much higher than the 80s in the other direction. Maybe I should plan a trip to LA after the class is complete in spring quarter. It can be assumed that these temperatures follow a normal distribution, so warmer days and cooler days are about equally likely. And the warmer they get and the cooler they get, the less likely they get in relation to that mean temperature. We can also use this equation right here for conversion from Fahrenheit, the stupid system we use in the United States, to degrees Celsius, the intelligent system that the whole rest of the world uses, that was developed by scientists, and all the smart countries were like, good job, scientists. Well, okay. And the US was like, we're jerks. No. I mean, that's the real history. Look it up. That's what happened with Celsius and Fahrenheit and stuff. US, not good at cooperating. What is the probability of observing a 28-degree Celsius day in June? Use the Celsius model from part A. Okay, there's a little confusion there because they did some editing. So we need the Celsius mean and standard deviation to answer part A. And then part B, just to think about why answers are similar or different when you're working with Celsius versus Fahrenheit. And part C, estimate the interquartile range of the temperatures in Celsius in June in LA. A little funky question. Now, to get part C done, we still need the mean and standard deviation in Celsius. There's a little confusion here for a lot of people. Let me show you where the confusion begins. It's in part A. Actually, for all part A and C we need the mean and standard deviation in Celsius for A and B, right? And heck, A and B, A, B, and C, all of them. Because we can't answer B without doing A, and can't do A without those two numbers. There's a little issue here that most people run into. Let me show you. Let's call it mean in Celsius. Is that good notation? Mean Celsius. There's no problem here. You just take the Fahrenheit mean, 77, subtract away. Let me make this bigger for everybody's eyeballs, especially my aging eyeballs. Subtract away 32 degrees. That resets you to the part of the temperature scale where freezing is. And then you multiply that by 5/9. that changes the size of the degrees Fahrenheit to the size of degrees Celsius, It shifts things around. Celsius degrees are bigger than Fahrenheit degrees, so it's an inverse fraction that gets that to work. Copy that, dump it into the nearest calculator. Mine is called Google's search engine, and the result is 25 degrees Celsius. Nice conversion, it's right on the money, 25 degrees Celsius, the mean temperature in June in LA, as would be understood by any international visitor to the city. The people in the States would go, huh, 25, how, that warm, is that cold? What's that in Fahrenheit? I mean, unless you've had some experience with Celsius, then you'd know, it's a nice, pleasant temperature. Okay, cool. The little issue is next. Calculating standard deviation. Let me show you. If I, as just an intelligent person, given the formula, go ahead and plug in the number. Standard deviation in Celsius. Okay, I'll take my standard deviation in Fahrenheit, which was 5 degrees. I'll plug it into the formula, so I'm going to subtract 32 and multiply by 5/9. Dutifully plug that into my calculator to get the arithmetic done. Copy. Hey, calculator, how you doing? Good to see you again. Paste equals. That's not right. What happened? Did I paste that in there wrong? Enter. -15. Review question. Can you get a negative number for standard deviation? It just doesn't make any sense. It doesn't work. Standard deviation is the average distance of temperatures on different days in June in LA from their mean temperature. An average distance has always got to be positive. So that's bad. And many smart people have come to me and said, Ralph, this is impossible. This is wrong. We need a positive number. Okay, so that's the wrinkle that many smart students before you have run into. And I think I've discussed this question every single quarter I've ever assigned it to any class. Now, there's a little trick here. Do you want the short, quick explanation, or do you want the drawing? You care? Want a little drawing, or do you want the short, quick explanation? No feelings. I have to choose the drawing or the short, quick explanation. I'll start with the short, quick explanation. When you take a temperature like 77 degrees Fahrenheit and you want to convert it to Celsius, it does matter that it's 77 degrees is, let's say it's 55 degrees above freezing, right? Because anytime you've got the daily temperature, you can compare it to freezing, or you could compare it to boiling. You could compare it to 0 or any other number you want, but you're making there's like set points on the thermometer that are interesting. Freezing and boiling, and everything in the middle makes the scale happen. If you're at a specific temperature like 77, you got to account for where you are specifically on the thermometer, right? No drawing, just I'm pointing at my imaginary thermometer now. Okay, so that subtracting 32 is crucially important. It gets you, in relation to freezing, and then the 5/9 switches you from the size of Fahrenheit degrees on the scale to the larger size of the Celsius degrees on the Celsius scale. It just switches the degree size. No drawing, but little fingers for different size degrees. Okay, now when you're talking about standard deviation, this 5 degrees Fahrenheit standard deviation, that's not relative to freezing. That's just 5-degree variation. And really it's relative to 77 degrees because of the data here. But that 5-degree variation could be anywhere up and down the entire thermometer. My imaginary thermometer goes vertically. So that's just 5 degrees on the scale. to shift it to Fahrenheit, you don't have to locate it near zero by subtracting 32. That's also where the number went negative. You just need to change the size of the degrees from Fahrenheit to Celsius. So you just got to multiply the 5 by 5/9. That's it. That's the imaginary drawing, shortest possible explanation. No need. It's wrong to subtract 32 here. 32, since we need just that sorry, that 5-degree Fahrenheit interval, right? So we don't have to interval to switch to degrees Celsius. We just need to rescale. And that is done. Standard deviation of degrees Celsius here, just 5 times 5/9. No need for the minus 32. It's not relative to freezing. It's just 5 degrees on the scale. Got to rescale it to the other degree size. So once people know that, they've got the correct standard deviation. Part A is relaxing. You can just plug it in and use your normal calculator to answer part A. Though part C is still kind of interesting. That was the original question that someone was interested in. That's 25/9. Let's try my arithmetic. 9 goes into 25 twice. And the remainder is 7. So that's going to be 2 point, lots of sevens like that. So I can round that off to 2.778, maybe 2.78, just round it to 2 decimal places, degrees Celsius. Yeah, and that's 25 degrees Celsius. Okay, cool. Now all the problems are doable. Let's focus on C. Okay, estimate the interquartile range of the temperatures in degrees Celsius in June in LA. All right, degrees Celsius interquartile range. Okay, let's just flip back our minds to chapter 2, section 2. We learned about our 5-number summary and the related, it's a measure of spread related to that. Our interquartile range is always the 3rd quartile minus the 1st quartile. And I'm here in LA in degrees Celsius. Wait, so let's say temperature. The book likes the little squiggly line to say, let's define the temperature as a normal distribution, capital N, or just norm for short. The mean is 25 degrees Celsius. Hey, I want a dang old capital. All right. The standard deviation is 2 7/78 degrees Celsius. Okay, cool. And now it's just like a problem from like back when we were talking about the normal distribution and using the probabilities to figure things out. It's just that it's a little funky because we need the 3rd quartile and the 1st quartile. We got to do 2 calculations and then do some subtraction. But quartiles we need those quartiles. And so now I'm in a world where I need to know a percentile in the world of the normal distribution. I'm going to slow it down to Ralph's speed, meaning I'm going to grab a pen. I'm going to draw. Which of the colors of the rainbow, or at least my pen options, reminds you the most of Los Angeles, California? Sorry, my phone was buzzing. For me, it's purple, the color of the Los Angeles Lakers, the most hated team by Portland Trailblazers fans, for numerous historical sports reasons. So I'm going to draw a purple curve. I'm in the normal world. I'm gonna label the center 25 degrees Celsius. Just a nice 25 right there. Friend, oh, I see, 25. And I'm gonna label my standard deviation. That's from the center, about that far, 2.78. Make my notes look a little classier by getting the numbers to line up with my marks better. And I'm remembering to find a percentile. That's the area below the curve. The third quartile is which percentile? What percent of area is below the third quartile? This was on our lab last class, wasn't it? If you're at the third quartile, how much area should be down below that value you're at? I only heard the 1% over the computers. Sorry. Oh, that's first quartile, 25. Third quartile, where I'm at, 75. Yeah, great. And 75% in the chat as well. Great. Oh, hey, good. I'm glad you made it through the technology headache, direct messenger. Welcome. So my third quartile, I can just kind of guess how it would look. Grab a pen, maybe 3/4 of the area here. Something like, I don't know, something like that. That should be my third quartile right there. Q3. And then the area I'm looking for is the area below that value. See that 75% of the area artistically drawn at human speed. So I learn a little bit more about how it feels to calculate and think about area with this kind of a probability distribution. And then in my notes, I'm going to write 75% right there. That's my area. Yeah. And now, no problem. That's my little graph. I just need it to look just like that over in GeoGebra to get the third quartile value. So right over to my buddy GeoGebra Classic via our links page, so I don't have to type anything. Hey, GeoGebra Classic. I wish I'd maintained my personality better throughout life so people could call me Ralph Classic. Nobody calls me that. I'll ask a few of my old friends if I'm similar enough to my youthful self that I could be called Classic. All right, normal distribution. We're here. Reset our mean and standard deviation. They're right there in my little illustration, my notes. 25 degrees Celsius mean June temperature in LA. I could type as many sevens as I want here for accuracy, or I could do it just like my notes, 2.78. Either way. And then I'm going to look, value's got to be, the area is below for a percentile. So look for the left-sided area. Come on, little buddy. Are you selected? Yeah. And then I don't want to put my number, my 75% in that first phase. That's the numbers on the scale. The area values go here in the very last box. 7/500ths right there. How's that for a calculation of the third quartile? And for my notes, to save everything, I'm going to grab my little drawing. Oh, hey. I'm going to grab my little drawing and all of its labels if I can successfully grab them all. Yeah. And just put it right there. Grab a shot of that for the notes. That's the detailed calculation of a third quartile. 2 steps there. Just remembering a third quartile is got to be above 75% of the probability area, and then getting it calculated carefully and accurately using technology. Good old technology. First Q3. There's my calculation. I'm going to just save us some time. I'm just going to change the 75% over to 25% to get the first quartile. So bye-bye, third quartile. Hello, first quartile. Great. Get a picture of that. And now I've just got to do some good old subtraction. Right? Interquartile range is going to be hey, buddy, what does it say? 26, I'm going to go 26.9 degrees. I'm going to round that off to the nearest tenth of a degree. 26.9 degrees is the third quartile. So warm days in June. Make this a little bigger so I can read it. Subtract away 23 and 1/10 degrees. That's going to be 3 and 8/10 degrees Celsius. There you go, interquartile range of LA June temperatures. So half the days in June in LA, the temperature doesn't vary any more than like slightly less than 4 degrees. That is some consistent, nice weather. And good luck recovering from the horrific wildfires, friends, in LA. Hopefully by June, people will have their stuff, mostly lined up and taken care of, and whatever's getting rebuilt will be on the path. Yeah, great question, because there are a couple of complicated wrinkles here in number 9. The wrinkle of the whole question is that standard deviation issue. The formula has to be adjusted to just focus on an amount of distance rather than an actual point on the thermometer. And then part C, it's a little more complicated when they give us an old-fashioned idea to then engage with to go figure out 2 numbers to answer their question rather than just 1. All right, yeah, great question. Great times with the normal distribution. Keep all the good homework questions coming. Remember, it never matters if you're on the most recent assignment or one from 4 weeks ago. If you've got a question, it's always good to ask anytime, any place. In the room here with us, over in the cubicle before class especially, or if you want to make an appointment and hang out and talk about stuff on after class days. I have a little time between 2 and 3 almost every week. And as long as you don't mind me eating while we talk. And there's other people who have appointments that are kind of standing, so I won't mention those times because those are kind of taken. All right, cool. Great work, everybody. All right. Oh, I love a homework question. And now let's go chat more about topics. Did you all get the fun email that I got? I think it was on Monday or Tuesday. Did you get the fun email? Do they send the students the email when the guy retires who nobody likes? Do they do that? Oh, it's great. My least favorite boss is not going to be here after June. So great. It's going to be nicer at PCC to never see the smiling face of that horrible man who hurt so many people ever again. Goodbye, Kurt. Professional tip. Don't hurt people at your job so nobody will be happy and wish you ill in your retirement. Yeah. Professional tip. Be kind and thoughtful, supportive. You could do it if you want. Whether you're a worker or a boss. Ah. Just sorry, it's the little squeaking and the smiles are just about when people who hurt people were to quit their jobs. It just makes me happy. Okay, sampling distribution of a sample mean. This is complicated. This is one of the most complicated ideas in the entire course. It's here because it's super duper whooper mooper. I'm trying to add more ooper rhyming phrases. It's wildly important to statisticians. This idea, being able to describe how whatever that long phrase means works, is fundamentally important for the analysis we do in statistics. For people who want to be nurses, business persons, psychologists, or work in related fields and need to take statistics on their path through life, this is something you'll probably never see again, at least not in this kind of detail, though the big idea behind it is conceptually important and useful to think about. So I'm going to try to split the difference of showing you the details that the statisticians who wrote our textbook want to share, while doing my best to emphasize the big idea, the big concept. That's the important thing. And then, we'll work on homework because that's what our statistician friends have given us to work on, but we'll try to emphasize the big idea. Okay, first thing to do is just parse out the title of the section. It's complicated. Sampling distribution of a sample mean. Quite a mouthful. Let's take it one phrase at a time. Sampling, that's something normal that we talked about a lot in chapter 1, right? The goal being, if you've got a population you'd like to study and you're unable to do a census, your choice of a sampling technique will determine, how representative your sample from your population will end up being. Goal being to get an unbiased sample that is as representative as possible of the larger population. Does anybody remember statisticians' most crucial requirement to get a good sample? The process should be blank. It was chapter 1. It was weeks ago. Yeah. What's better, for me to sample you all as statistics students, or for me to take a random sample of statistics students from all over PCC to learn more about statistics students? Which one's better? Just you all who I'm working with, or a random sample from the larger group? Second option. When I say it out loud and give you the choice, the random sample is clearly the better option. I've got a better chance of getting a more representative sample when I use random sampling. So sampling here, they mean random sampling from a large population, okay? Distribution, that word is shorthand for probability distribution. So we're going to be looking at numbers and their corresponding probabilities, okay? And then the last part of the phrase, it says of a sample mean. But that's crummy language choice to get at the concept here. Okay, let me pick a number out of my hat. We just talked about the average temperature in June in LA being about 25 degrees Celsius. Okay, if you go to LA in June on, say, 5 random days from June, from this past June, and then 5 random days from the previous June, and 5 random days from the previous June. See what I'm saying? Just taking random 5 days from various LA Junes. Are they all going to have the same sample mean temperature? Is it always going to be 25 degrees for 5 randomly selected days? No, I mean, sometimes you'll pick 5 random days, a couple of them were noticeably cool, so your sample mean will come in below 25 degrees. Sometimes you'll pick 5 random days that were maybe 3 of them were during a heat wave, so your sample mean comes in like over 26 degrees, like up there near the top of that interquartile range maybe, or even hotter if you pick 5 random days that were all hotter than average. Sample means are going to vary from sample to sample. And so when they say sampling distribution of a sample mean, that's a long phrase that's short for something still longer. It's the probability distribution of how sample means should vary from sample to sample. It's a probability distribution that shows how a statistic varies from sample to sample. That's the concept. Because if you have a good way to analyze how sample statistics vary from group to group, you get a lot of analytical power to talk about putting some wiggle on an estimate to get a margin of error. It gives you analytical ways to do hypothesis testing to get a sense of how likely your sample data looks under some assumption about the population. So a sampling distribution That's always for how some statistic varies from sample to sample. And in this discussion, we'll focus in on how sample means vary from sample to sample. That's the sample mean is short for that much longer phrase. Sample means varying from sample to sample. It's like how, mathematicians say, let X be a real number. What they mean is you can plug in any number you want for X, or any number that makes sense would work here that solves an equation. Mathematicians just use often not plural phrases to describe things where there's lots of options. All right, that's the big concept. We'll keep pointing at it the whole way. Oh, hey, thanks for the random in the chat. I didn't see that back during the thing. Oh, and hey, I didn't see a couple of chat comments. Yeah, I'm joining the Buy Kurt party, obviously. I really want to go to the retirement party. And if they have a card, you can like say a little note to him. I really want to write him a little note. Short one. Bad job, Kurt. Won't miss you. You know, shouldn't have been so harmful. It was not a good idea. Meanie. You just kept trying to cut our pay and maintain all of the worst parts of our working conditions every 2 years. What's his thing? That's why he kept getting raises. All right. In any case, the central limit theorem, this is the analytical gemstone for statisticians. It's the theorem that analytically describes how statistics vary from sample to sample. And it sits in this really important place in the universe of statistics. CLT, short for the central limit theorem, it joins together all of the work we've done, like back in chapter 2, really, where we were looking at summary statistics for samples and graphical displays of sample data, whether it was numerical data, and we looked at means and standard deviations and 5-number summaries, along with a graph like a histogram for a large data set, or a beloved dot plot for a small data set, or, if we're in the mood for a box plot to compare some multiple data sets, lots of options. If we were studying categorical data, we'd focus in on proportions or percentages to summarize how things are distributed among the different categories. And we could look at a bar chart if we're just feeling like fitting in with the statisticians, or, if we had a small number of categories and they look good on a pie chart, or there's other options as well. So lots of ways to look at sample data and understand what you've learned. And it's when we have a trustworthy analysis of how samples vary from sample to sample, how statistics will vary, that lets us do what's called inferential statistics. This is where we're headed in chapter 5 of our textbook. That's when we use sample statistics to answer, or at least address and analyze questions about the unknown characteristics of the population parameters that researchers really care about. The two main methods for that are confidence intervals. So if you've got a sample and you've got a mean value for, say, that particular June in LA, the mean temperature was 23.6 degrees. Well, you can put a little margin of error on that and you can see if it looks like a reasonable, that's confidence intervals. Estimates with margins of error. The margin of error depends on how things should vary from sample to sample. Hypothesis testing we can also do. Once we're sure we've got a random sample that meets a few conditions, we can make an assumption about the population parameter, whatever characteristic it is, and then see how likely our sample data looks in that setting. That can provide us with evidence against our assumption, or it can just, we can let the assumption be if we don't have any evidence against it. And we'll look at both of those topics in chapter 5. Those are two of the topics that are important for you as people on your path toward your programs. Those are the techniques that get used in research all the time to analysis about large groups based on samples. Gosh, I want to do one more. Love that Buy Kurt comment. So great. I'm so happy. When I retire, I hope everybody who doesn't like me will be so happy. It's gonna be so great. And I hope the people who like me will also be happy. Like, it was nice to work with that guy. And that'd be great. I'm kind of divisive, so it's gonna be some of each. Number of basketball games attended. This is one way of looking at how this theory works. You start with a population and then see how the act of taking lots of samples plays out. That's what they've set up on our slides. Here's some population data. We're going to focus in on just a group of people who have attended some basketball games somewhere. Hey, it was good that I said Lakers earlier. They're a basketball team. But I bet these are people from North Carolina, where our textbook is from. So I'm guessing they went to go see college basketball games mostly, because they're probably mostly college students who are like a convenient sample for their stats teacher. Bonus little review question. Is the distribution symmetric or skewed? And if skewed, which way? So get on your... Oh, and bonus review question. Can we estimate the mean value, the mean number of games attended, just with our eyeballs? That should be the balance point if we view that histogram as having some weight. Let's take them one at a time. Symmetric or skewed? So skewed. Is it skewed left or skewed right? I didn't hear that because two people talked at once. Yeah, skewed to the right. The symmetric part of the graph is really that very big bar from 0 to 10. And then the people who went to more games than 10 are skewing the data set away from symmetry off toward the right. And hey, we've already got someone's estimating the mean, looking at their eyeballs at about a 7. So let me just get my mean sketcher here. You know, I like an orange triangle. There's 5, maybe 7's right there. What do y'all think? Is that, you know, you got to be above the halfway point of that big bar, at least a little bit. So 7 feel good for the first shot at it. Yeah, somewhere between 6 and 6, 7, 7, 6, 5. It's more than 5. It's less than 10. So 7 is a great guess. And I'm going to take a couple notes up here at the top of the page. Oh, whoops. A couple notes before we go look at sampling distribution options. Where's my pen? There it is. I'm going to put them in red for the population. It's skewed right a lot. You know, like it's totally skewed to the right. There's just the big, you know, tall 0 to 10, and then everything decreases as you go further and further to higher and higher numbers of games. Mean, we're estimating it around 7. Oh, and what's the range from the lowest number of games to the highest number of games, just so we have an idea of the spread as well. Yeah, just the last number on the graph is 70. I'm not going to be any more creative than that. I don't know if I'm guessing it's one person who saw between 60 and 70 games. I don't know if they saw 65 games, 67 games, but 70 is the last number on the scale. So a perfect guess or, you know, estimate of the range. Great work. Okay. That's our population. We come back and look at the population as needed. Now let's go look at what a sampling distribution looks like. Here's one. This graph, the sampling distribution of the sample mean. Remember, conceptually, that means this is how many different samples means are distributed. If you take samples of size 10 again and again and again out of that population, take the mean number of games from just 10 people from this population, do that thousands of times using a computer. Computers are really good at, if you say, this is the population, do something again and again and make me a graph, right? So this is, you can see like on the scale here, the numbers are in, the tallest bins are like over 1,000 samples whose means fell in various ranges. All right, that's how it looks. Okay. What does a single observation in a sampling distribution represent again? What would one value in that world be of this distribution? Oh, I see the question. Does this mean the sample was repeated 10 times? Good question. The n equals 10 means each sample they took from this population. So if you take 10 random people from this distribution and you take the mean number of games they went to, and then you do that however many times up into the hundreds in all these different bins, that's probably thousands of times, maybe 5,000 or 10,000 different samples. Each sample has 10 people from the population, and you get their mean number of games.
Wait, so you're saying this graph is like you took the last one and you split it into groups of 10 people and you put the mean of each of those groups and then you plotted those means?
Very, very close. It's like we took this group, the whole group, there's probably about 200 people here.
Sure.
And rather than split them into groups of 10, it's from all 200 of them, grab a random 10, consider the mean number of games for this random 10, throw it into my sample means list, put them back, grab a new random 10, take their sample mean number of games. Yeah, with replacement, exactly. So it's sampling with replacement, groups of 10 at random, thousands of times. For each group of 10, we've got their mean number of games they've seen, graphed like this. That's the graph. Great observation in the chat. Yes, that definitely in drawing thousands of samples, people could get sampled more than once. Yeah, so someone could end up in more than one sample, and that's definitely true. Because like, say up here, this like very highest sample mean is somewhere between, I think it's 16 and 17. That had to have one of those very few people who saw a ton of basketball games in that sample to get the mean up that high. Whew. But let's just see how the slide phrases their answer. Each observation here, remember, is one single sample mean, symbolized by X with a bar on top, X bar, as statisticians pronounce it, from a single sample drawn from the population on the previous slide of size 10. One at a time, but a computer can do it thousands of times and make us a lovely histogram of thousands of samples means and how they're distributed, a sampling distribution of the varying sample means of size 10. This is another place where if I could be the dictator of statistics, I would change the name. It wouldn't say sampling distribution of the sample mean. It would say sampling distribution of varying samples means, right? Or different samples means, because that's what's happening. There's more than one thing happening here. Someday, dictator of statistics, my dream. Or maybe, I don't know. Okay, now there's questions about comparing this graph to the population. Is the variability of the sampling distribution here smaller or bigger than the variability in the larger populations distribution? And remember, previous graph, we got range 70 for the whole population, from 0 all the way up. I got a hand signal in the class. Someone said smaller. And we can see here the range for this sampling distribution. Let me take a little note. I'll just say n equals 10. The range is, looks like the lowest bin here is from like 1 to 2. I think, yeah, 4, 3, 2, 1 to 2. And the highest number I can read on the graph is like about that between 16 and 17. So I'm going to go 17 minus 1. And I'm going to call the range about 16. But if someone had just said 20, I would have said that's a good one too. Just reading the biggest number off the graph is also a good estimate, but closer to that. See why the range is smaller for the samples means? Just how averages work, right? If you get even those two people who went to tons and tons of games into the sample or into one sample, they're still going to be added to people who went to most likely between 0 and 10 games. And then when you do the division by 10 for the mean, it's going to bring the large values down closer to the small values. Also, it doesn't go all the way down to 0 games anymore. It starts at 1. Because, if you pick someone who went to no games, well, chances are they're going to get averaged in with at least a few people who went to a couple games, one between 0 and 10. So somewhere in there, you're going to bring the averages kind of, I guess, closer to the population average. Make sense? Okay, let me see. Smaller, okay. Oh, and we had questions on the previous slide. They didn't ask us here, but let's try them. Symmetric or skewed? These samples means, are they symmetric or skewed? Say that a little louder so I hear better. Yeah, still skewed right, but what do you think? As much as, less than, or more than the population? Yeah, a little less, because now our peak is there's a couple of lower sized bins to the left, while there's still tons of bins getting smaller and smaller off to the right. Skewed right, not as much. So put that in my little notes here. Skewed right, less than pop. And for the mean value, all right, mean value estimators. I'm going to grab back my little, my beloved little triangle for estimating means. Can't be this low at the peak and fall off to the right. So it's got to be above 4.5. 5.5. I don't know. I'm just eyeballing this with my eyeballs. Would people buy that? 6-ish? 6-ish? Like more than 5, less than 10, just like the population. I came in kind of close to 6 with my eyeballs, but someone else's my eyeballs might come in a little bit closer to 5 or a little bit closer to 7, I'm guessing. If we did a little activity, we could have more, but mean, let's call it close to 6. Yep. It's eyeballs based on Ralph's eyeballs, which is not at all far from our estimated mean in the population. That was 7. And on these pretty large scales, that's being just off by 1. Those estimates are pretty much the same as far as I'm concerned. Kind of cool. Okay. Wait, let me reshuffle my little notes up here. Population was the first one we saw. Then we saw this n equals 10. Sampling distribution. Okay, now let's compare our sampling distribution of the mean. So that's of varying means from thousands of different samples of size 10. That's the graph we see at the lower left from the previous slide. To the sampling distribution of varying sample means for thousands of samples of size 30 here on the lower right. How did the center, spread, and shape of the distribution change as we shift from samples of size 10 here, like we just looked at, to samples that are larger, 3 times larger, size 30? Should we just take them in same order as our notes? Let's do that. Get up to samples of size 30. First question, symmetric or skewed? I'm with you. It's not symmetric. It's a little skewed and still to the right. Yeah. So I'm just going to say skewed right. A little. Same language. I don't know what the technical word would be for a small amount of skew. Mean value. We can estimate that again with our eyeballs. Anybody else other than me want to take an estimation there for that? This distribution down here, if I'm going to put my little my beloved mean value estimating triangle at the balance point of our sample means from samples of sample size n equals 30 graph, where would this little guy go? If I move it back and forth slowly, will that light up your eyeballs? Oh, we've got one in the chat. About 5.5. 5 is here, 5.5 is there. Or so. People like it. Pretty good visual estimate, 5.5. Dang close to our 6 from the previous one, which was dang close to 7 from the previous one. So our mean estimates are coming in within 1.5 of each other on all 3 graphs. That's pretty cool. So let's get that in the notes. Mean close to 5.5. Cool. And the range, I'll do the subtraction. The lowest bin with sample means in it that I can see starts at around, I don't know, 2.5-ish, and it goes up to about 10.5-ish. That's a range of approximately 8. So just all the way across that skewed distribution, the simplest variability estimate is range. It can be difficult to estimate things like standard deviation or interquartile range from skewed graphs. So I like the range here. Okay, let's see what the slide says. Center, about the same. All right, yeah, I'm with that. Spread is smaller, definitely. We got the range about half as much. And the shape is more symmetric. Well, we noted it was less skewed, so that's the same thing. Interesting trend developing here. Let's go to one larger sample size. Oh, and we're almost to the break. In about 5 minutes, we'll take our break. I think we're just about through this first. Oh, no, don't lose all that. Just lose that. Okay. Oh, in the past, during this discussion in a remote class, I kept notes with a little bit more rainbow coloration. So that was in spring 2022, and I just took some snapshots of that discussion to have some of the notes on the screen just be in the slideshow for the future. So pretty similar takes that we have today. But here's another sampling distribution. Now the sample size is 70. And again, it's thousands and thousands of sample means, samples of size n equals 70. Now, it's not that hard to make our n equals 70. We can just go down the list. Symmetric or skewed? Symmetric enough, yeah. I depending on how you draw the bin edges, it'll look more or less symmetric if it's truly symmetric, but that looks, if I drop my wet noodle on there, it's going to give me a bell-shaped noodle. The mean value, no pressure on anyone to add a number to this. My guess would be 5 3/4. Does that sound good? Like, I'm just going to the middle of that tallest peak. Maybe it'd be closer to 5.5, so maybe 5.6, 5.7. I'm going to go 5.7. Oh, hey, and as I say, I'm going 5.7. Manjula types that in the chat, so we have agreement. People are typing and saying the same thing. That's great. And the range here is small. I'm just going to take the numbers on the graph. That's 4 and then a half more, so 4.5 is the range. So noticeably smaller range. Okay, now. So see the trend? Bigger the samples are. See the trend? What happens to the shape of the sampling distribution? Just put it here. Bigger samples create sampling distributions that are less skewed or more symmetric. Great. Okay, did estimating the mean get easier or harder? I mean, for me, finding the balance point visually is always its own little challenge. But it sure is easier to read the number off the scale when the range is littler, right? So it's with less variation, it's easier for my eyes to go to the center and also, or find the balance. And also, heck, the more symmetric it gets, the more visually obvious the balance point gets. So I'm gonna say easier to see the mean of all the means. Or in the population, I guess it was the mean of all the individuals, but think of them as being samples of size 1, right? And then you don't have to type or answer, but the range is getting smaller and smaller range. That's more and more consistency for the varying sample means as we go to bigger and bigger sample sizes. Means are more consistent. That's less variation or variability, right? And again, what I want to focus on here is the big concept. This is like if you're in a normal world of research where like you have a budget, you're going to do a study, you've gotten the thing funded, most research, you're going to only have a few chances to draw your sample out of your population for your study. I mean, think of doing a drug trial. You've got to find people to participate and do all the work to get people into the treatment and placebo group and have a big enough research group. There's funding, it's complicated. You get like one shot to estimate the difference in response to this drug. Now, these sampling distributions let us have an analytical tool that says, okay, if we've got this mean from one sample, as long as we're confident we've got a random sample, as our sample size increases, we can be more and more confident estimating things or talking about how this relates to the population, because we have this theory that says the bigger our sample is, the more likely it is to be near the population mean, the less likely it is to be very far from the population mean, and the more predictable and consistent the variation should be in terms of symmetry. So it's getting more consistent in multiple ways. More symmetric makes it more like a normal distribution. And we have all these powerful math tools to use those. Less variations, just great when you want to estimate stuff. And it's easier to see the population mean. That's the mean of all the samples means is the population mean. So it's just this really powerful analytical tool that bigger samples are better, not just because there's literally more people from the population, and that's good for just having more representation, but because analytically, we're more confident that we can talk about population parameters with actual like math to back it up, nerdy level nerd math to back it up. Yeah, that's the big story of the central limit theorem, told with some graphs. But that little list there is crucial for the conceptual understanding of what statisticians care about here. Bigger samples, we expect statistics to vary more and more consistently, both in shape and in variation, like of the values of the stats. So cool. And I think if I'm right, we're just past, like, it's time for a break, but I think, well, you know what, let's just have the break and then I'll double check what the quiz is during the break. If it's what I think it is, we'll take it right after the break. And if it's something else that works better later, we'll talk about it later. So I'll figure that out on the break. See you back here in 10 minutes. That's going to be about 15 minutes past the hour. Cool. Yeah, all these notes, there's various versions of them on the slides. It's cool. Let me
If I understood it, but I was like, Cass.
Yeah, I'm not.
I thought I was like, I feel so powerful that I'm having to help Cass right now. I feel like I'm not.
Oh.
Yeah, that's just not like. The numbers, yeah. It can be complicated.
Even in series class, you do that.
Yeah.
The numbers.
Did like a video game history education in your generation? No.
Probably not. Yeah, some people don't have any interest in video games at all. That's normal. I gotta tell you, Parappa the Rappa, if you want to learn one of the great turning points in video game history. Parappa the Rappa. A little dog. A little dog who had a crush on a little cat. And to win her attention and have a good day, he had a lot to do that involved a lot of rapping. And it was the first game where you did like rhythm, the first rhythm game that was like well known, at least in the States. I've been listening to some of those great raps. Great. It's got I think it's the only video game where one of the level bosses is not losing control of your bowels. That's a cool. He eats a cake he probably shouldn't have eaten. He's not a good cook, part of the plot. In any case, we're back. Good times. Great oldies. All right. We left off. We had just looked at these various sampling distributions of varying sample means from thousands of samples drawn at random from this very, very skewed to the right population of basketball game watchers, or the people in there who hadn't seen any basketball games, whether from lack of interest in basketball game viewing or just because they didn't have time, because it takes a whole night to go out to a basketball game. It's a big investment in time, and it's not inexpensive to go to the basketball game. Okay, now I was right. The quiz is now. It's quiz time. You ready? I'm ready. Let's take a quiz together. I'm heading to D2L, Brightspace, coursework, quizzes. It's gonna look like I already took the quiz because I peeked at it before. But there it is. It's got a great creative name. Sampling distribution of a sample mean quiz. Details, boring. For me, it's continue quiz because I stepped away. For you, it's probably start quiz. And looky here, as sample size increases, the sampling distribution of sample means for samples drawn from a population with any distribution shape that's skewed off to the right, like the population we looked at. Could have been skewed off to the left, same trends would have happened. Could have been a symmetric population, could have been a multimodal population, as long as the samples are getting bigger and bigger. There we go. What did we see? Either less or more variation and symmetry as the samples got bigger and bigger. It is very wordy, good observation. I don't know how to decrease the words without losing track of the idea, because it's actually complicated.
Less variation, more symmetry.
Does that resonate? We're getting some nods in the room. Did people hear that? Oh yeah, it's in the chat, typed up the moment as it was being said in the room. It was being typed in the chat. Everything's happening. Less variation. That's right. Things got more and more consistent as far as the means not varying as much for larger and larger samples. And it got, well, it started off skewed to the right in the population and got more and more symmetric the bigger and bigger the means got. So don't forget, if you like the eyeball version is less variation, more symmetry. Where's my pointer? Give me my beloved pointer. Bam, second option there. Be sure to select that. And then you want to submit the quiz to get your point. I never submit these quizzes because I don't need any points. Points aren't going to help me out at all. They might just slow me down. You know, if I want to look at the class average, because I wouldn't get all the points. You know, I wouldn't do all the assignments. All right, cool. Get the point. And hopefully, more importantly, we're getting the point, the big concept here. As samples get bigger and bigger, statistics are more and more predictable in two crucial ways. The shape of the statistics distribution is more and more symmetric, so more and more like a normal bell curve. And with less variation, that makes things, margins of error smaller for estimations. That makes us our evidence looks stronger against a bad assumption in a hypothesis test, the bigger our sample gets. So these are important analytical tools that statisticians just really, really deeply care about. Okay, let's look at it like an example, a little question that looks kind of like a homework or an exam question. I'll get back through. I rewound a little bit in the slides. Let's get back to where we left off. All right, here's a practice. Look at that. At the top, here's a population. So let me just, there's our population, right? Oops, that's supposed to be a highlighter. There's our population balancing out at mean 10. And we can see the range of it is about 50, give or take. And they give us the standard deviation as well, 7. Okay. Now, they give us 3 plots below, plot A, plot B, and plot C, which are mixed up, but one of them is a single random sample of 100 observations from that population at the top. So think of that as n equals 1, the smallest possible sample size. Second option, a distribution of 100 sample means from random samples of size 7, so n7. And the last option, a distribution of 100 sample means from random samples that are bigger, size 49. All right, can you sort those out using what you know about how bigger samples means get distributed? Bigger the sample? Oh, it says it right in the chat. Less variation and more symmetry. Just knowing those two important concepts, we can sort out graphs like this for practice. I'll just wait upon you. Maxine?
149.
Oh, so you're saying you're nominating 7 here? A? Okay, yeah, let me line them up. So 1 for B, which is what you said second. All right, so let's put this one, n equals 1. I like the sample sizes for the labels the best. Plot C is n equals 49. That's all 3 people have suggested that, the third option. So here's n equals 49. And that leaves plot A as n equals 7. And I think I've got those lined up just like Maxine said aloud. My typed, and Manju is backing you both up on the third option. Does this look good to people? Oh, can I dumb this down? I can try. Sorry, when you asked me to dumb something down and I'm the teacher, I thought, okay, what am I dumb at? And then I thought of like all of the adult tasks in my life I fail at consistently. So just give me a second to think about my personal failures. That'll help me feel like I'm dumbing down. But that's not really what you meant. Yeah, I am drinking more tea. But no, I know what you mean. Just to get the idea back here. The trick here is, let's just get the note at the top. Bigger samples have sampling distributions, a long phrase, right? With, it was well written in the chat as concisely as possible, less variation. So that's going to be smaller range and smaller standard deviation and more symmetry. And for me, when I want to sort through these, the first thing I do, oh, well, all right, you're feeling it. Okay, the brain fart is farted and you're getting it. But let me say, the way I look, if I'm gonna sort out three graphs like this, the first thing I look for is the most obvious thing. Let me highlight it for you. I'll go for a red highlighter. More symmetry is pretty easy for my eyeballs. This graph is the most symmetric of every graph on this slide. And I know that that's got to be the biggest possible sample. So n equals 49 goes there. That's the first thing I see. So I sort them out that way. So when I saw the chat that just said plot C is n equals 49, I thought, hey, that's how I do it. I noticed that first. The other two graphs, neither of them is particularly symmetric. I'll just use a pesto noodle instead. They're both skewed off to the right. And with 100 samples, you know, they both look fairly skewed. But then I'm going to look for, when I'm trying to decide between two that are skewed, I'm going to look for less variation. And I'm not even thinking about standard deviation. I'm just looking down at the horizontal scales. I can see plot A starts at 4 and ends at 18. That's only a range of 14 compared to the range of 0 to 35 or 35 total range for plot B. That's less variation right there. So that's got to be the littlest one. Wait, so do I disagree? I think N1 should be. Oh, no, wait. Sorry, I'm tired. I'm tired. Look what I did. I had the brain fart. Less variation goes with the bigger sample. You are all right. N equals 7 is bigger. So since it has less variation than n equals 1 should be expected. Sorry, I just confused everybody, not just myself. That's my bad. Less variation for the bigger sample. So if they both look skewed, I focus in on variation. The smaller, the more consistent samples means are associated with the bigger samples. Phew. Phew. Okay. And no shock, you're all right. Number one is plot B. Their short notes say distribution like population, like if the two graphs of the population and plot B look similar to your eyeballs, great. That's another way to see it. Plot A, they're saying less spread, but more importantly for plot C, still less spread and symmetric. So that's the trick. It's the less spread that gets me. For graphs that look the same, I look at spread to make decisions. For graphs that look symmetric, well, that's obviously going to be the biggest samples to drive those. Consistently symmetric samples means. Whoop. Whoop. Would that'd be a fair exam question, but it would also be a hard exam question, right? Or maybe not hard if you've practiced a couple times and you have your notes and you're clear on how this starts to work and it's starting to feel good. But when it's brand new, it would be a hard, I put you on the clock for a quiz at the end of class and had said, no notes. It might be hard because it's hard to unwind bigger, smaller, more consistent, less consistent, you know, at least for me. But yeah, more consistent two ways, both in the range and the symmetry as we get bigger and bigger samples. That's the big concept. Spring 2022 lecture version with the nice, beautiful rainbow color coding of spring 2022. Look at that. I put all the ranges there. Pretty classy. I did all the symmetries. I noted. I'm really thinking. We had a big discussion that day. I'm pretty proud of my screenshots. Where was I? Was I back in the apartment back then? That was long ago. Ooh. Okay. In any case, the central limit theorem, CLT for short, I mentioned before, it is the most important theorem in statistics, a crucial link between sample data sets, which we can do anytime in our research, and then if you want to generalize to a larger population, when you've got a good random sample, it gives us the analytical tools to do that. Here's the informal version of the central limit theorem for us. Central limit theorem for sample means as the sample size n gets bigger, the distribution of sample means becomes more normal. So not just symmetric, but also it's going to be, if you had a bimodal population, you'd end up with a unimodal symmetric sampling distribution of samples means, as long as the samples are big enough. And more consistent, that's a smaller range in standard deviation as we observed in all those examples. The caveats, the requirements for this to work are, got to be doing random sampling from a large enough population that you're not throwing off the mean while you dry out your sample. If you can take a sample that big though, there's like a little correction you can do in the calculations that nerdier nerds than I understand how to do. So a research team would know if you have a very large sample, how to make good adjustments to have the right consistency measurement. Kind of cool. There's a cool applet that demonstrates this like one sample at a time in kind of a cool way. Do you want to just see one more example? It's kind of a cute one. Kind of fun. It's like a boring video game. Let's look at it. We have time. So Rossman and Chance are two stats doctoral degree holders who share the little applets, the little online programs they've made to bundle with their very expensive stats book they sell. So if you want me to go to the much more expensive stats book, I can take it to the committee. I lied. I wouldn't take that to the committee. I want the no dollars stats book. But when we're here at this one variable with sampling applet, when we show the sampling options, let me make this, can I make this one step bigger on my screen like that? Too bigger? Yeah, that's a little bit more visible. Okay, look, here's a population model. Populations were red in all my notes, so let me get my red highlighter back. Here's the population on this side, this group here. We can choose the shape. In our examples, we saw skewed right groups. We want to just look at a uniform population where all the values are equally likely, just for a different flavor. So in this setting, with mean, the balance is 10, standard deviation set to 5. That takes us out to, I don't know, somewhere between 1 and 2 maybe for the minimum value in this population, and somewhere between, I don't know, 18 and 19 for the maximum value in this population. Every value on that scale between about 2 and 18 equally likely to show up. Okay, now for sampling options, we have some choices here. We can take as many samples as we like, and we can make them as big as we want. What's a good sample size in this world? 1, 2, 3, 4, 5, 6, 7, 8, 9. Plus 12 is 21. There's about 21 of us here today. So let's say we were going to sample as many people as us, and we were going to measure or count something where anybody from the population could give any answer. Maybe it's the day of the month we were born, something innocuous like that. But the months are only 18 days long. Now I can just draw a sample, and then the computer does some work for me. Watch this. It says draw samples, set that. Looky there. In the middle, this in blue, this is a sample. So it's one sample. You can see 21 little dots in that dot plot. And looky there, they even use a triangle, although it's not orange, to represent the mean with a little fulcrum. And you can see that sample of 21 values drawn with those completely the same likelihood from that scale in the population. There means 10 and 6/10 and a little more. And then graphed over in the statistic, this one on this side, this is our, I want a box. This is our sampling distribution. This here, see that? Sample means. We have one sample, it means a little bit above 10, a little bit above 10 and 6/10, and there it is, graphed all by itself, our sole sample. Pretty wonderful video game. Let's keep playing. I'm going to draw another sample. Okay, funky little sample. It's got a gap. I never would guess this thing's being drawn out of a uniform population if I didn't know. Its means a little lower, 9.5. And now we can see over here in our sample means world, we've got 2 sample means drawn, and the mean of the samples means is just a little bit more than 10 because we got One sample whose mean was higher than 10 and one that was below. Love it? Not as good as Parappa the Rappa in the history of video games, honestly. Let me draw a few more samples. I'm looking at the number of samples. There's 5 little samples. How about, let's get up to 10. There's 10 little samples. Most recent sample's mean is 9 7/10 or so, and it fits in among a few other samples means that are down there closer to 9.5 than 10. That's kind of cool. Okay, that number of samples control at the top, 1 at a time is not very many, so I'm going to pump it up to 10 at a time. Draw some samples. Now I've got 20 samples means graphed in the blue box. Some more, 30, 40, 50. There's 50 samples means in the blue box there, graphed together. Samples of size 21, 50 samples. And you can already see, look at that. It's kind of symmetric after just 50 samples. Okay. Well, I'm greedy, so I'm going to do 50 at a time instead of 10 at a time. So I've got 100 samples, 200, 300, 400, 500 samples. Check that out. We've now got a dang unimodal and dang, fairly symmetric graph of samples means. And the mean of the samples means it's about, well, 10 1/10, which is pretty dang close to the population mean. I'm going to get more greedy. I'm going to do 500 samples at a time. So I've got 1,000 samples, 2,000 samples, 3,000, 4,000, 5,000. That's probably about the scale of the sampling distributions we saw in the slideshow. It was thousands of samples. And now, if I grab my good old symmetry judging noodle, what is it, marinara? Let's go marinara still. That is symmetric. And notice that our samples mean, so the mean of all 5,000 samples means is like just a little tiny bit higher than 10. So this thing is balancing out. 10 is almost exactly in the middle, just like the population. The theory plays out again and again in this randomized world. So, I mean, we just got a little peek at how this looks in more detail than those slides versions, at least as you generate one of these graphs. Kind of cool. Thanks, Rossman. Thanks, Chance. And how cool is the last name Chance for a stats professor? I mean, Beth Chance. She must be so psyched. When did she start to feel psyched about it? Like, was she young, or like she already have her grad degree and she's like, just stop telling me that, everybody else. I don't care that my last name's Chance. It was random. And then she'd giggle because she made a point about. Yeah, but this is a cool way to get another sense of how this works and how it looks. And there's one more little mystery here that I think this graph gives us that the previous examples didn't. We can see really clearly, this is nice. The mean of 5,000 samples means is dang close to the population mean, right? Now the population started out with standard deviation 5. Its range is about, I don't know, 2 to 18 or so. But look here. Now we have this standard deviation. It's about 1 1/10, 1.094, and the range is down to about 8. So it's shrunk down. How much? What was the shrink factor, you know? And that is described back in our slides as part of this theory. So, and it's going to be crucial for some of your homework questions to make this adjustment to figure out how this standard deviation works in relation to the population standard deviation. We got to shrink that number down if we want to talk about likelihoods of seeing various sample means. Oof. Okay. I'm going to lose all my red and blue stuff here. Or wait a minute. No, maybe I want it. I'm gonna screenshot this thing. I'm taking a picture of this specific, because I like my boxes and my red stuff, but we're gonna lose them all when we go back to the slides. So they're gonna live forever in our class notes. Oops. Yeah, right here. Sampling distribution applet example. Just in case I think I might want to look back at this when we see one more thing on the slides, but I don't want all that red and blue stuff in our way before we get there. Now it lives on here. Cool. Okay. Okay. Cool applet. Thanks, Rossman. Thanks, Beth Chance. Good job. Maybe, put some energy into creating some lower cost materials to share with stats learners. That would be a really cool thing to do, especially if you're already wealthy professors at fancy universities. Of course, that's how they got wealthy. They wrote textbooks. But here's the formulas, and this stuff's not surprising. I think I made a slide that has a drawing. Yeah, let's look at the slide. The drawing helps me talk through these relationships. Okay, 3 important facts about the distribution of varying sample means. Shorthand, just X with a bar on top. They just use the X with a bar, can be shorthand for the entire probability distribution of varying sample means. Consider taking a simple random sample from a large population, and you get these 3 cool facts. The mean of the sample's means, notation in our book is Greek letter mu, subscript X bar. I just write mu in my notes usually, the Greek letter. It's like a U with a tail on the front. But the cool thing is the mean of all the samples means is going to be the population mean. So mu, that symbol with no subscript is just population mean. Our varying samples means, unsurprisingly, some are going to be bigger than the population mean, some lower, and the bigger the samples get, the more that plays out. The standard deviation of the distribution of different samples means is denoted by sigma with X bar for a subscript, sigma standard deviation of varying samples means X bar. Well, this is how you get that number. You take the population standard deviation, sigma, and you divide it by the square root of the sample size. So like right back in our, and we can double check that this works perfectly by just looking back at our previous example from the applet. Here, if I just say, okay, the population standard deviation is, let's say, standard deviation of sample means. It's got this formula, sigma, subscript X bar, and that's a Greek letter and an X with a bar, but I just type it all out like that. It's population standard deviation divided by square root, SQRT and computer ease, of the sample size, n. Plug in our numbers here. That's 5 population standard deviation divided by square root of 21. That was my arbitrarily chosen medium, small, medium, big sample size. Throw that into my calculator. And looky there, 1091 rounded off to 3 decimal places. And then if I look back at the notes, that's only off. The predicted standard deviation from the theory is only off by 3 10,000ths from the simulated version with 5,000 samples. So cool. It plays out as expected. You can ask questions about how likely would it be if that's your population to have a sample whose sample mean was 12 or higher, to have a sample whose sample mean was below 9. These are the kinds of questions that, well, there are settings where they're meaningful, and we'll talk about a couple of them in the next few minutes. So let me just, maybe in my notes, typed that. Copy it. It's typed. It was part of the discussion. Notice, like that little fact, formula for STAT. The formula is great. It's great. Sorry, the standard deviation or means formula is great. So cool. Good job, nerds. You really came up with a cool theory and you should be proud. Good job, statisticians. And then here's a question where there's actually a reason to use this kind of theory in real life. It's from manufacturing. A manufacturing process is designed to produce bolts with 1/2-inch diameter. Okay? Once per day, a random sample of 36 bolts is selected. Say their factory is open for 9 hours, they could just take one bolt off the production line every 15 minutes for a systematic random sample. Or they could, out of a giant bin of all the bolts of the day, have a robot grab 36 from random points in the big bin. You know, any way that random sampling works. Then they record their diameters, using very accurate measurement devices that can measure things to the 100th of an inch with accuracy. Take the resulting sample's mean. If it's lower than 49/100ths of an inch or greater than 51/100ths of an inch, that means their bolt manufacturing machine the tolerances are going bad. They're making the bolts either too small, if the average is lower than that range, or too big, if the average is bigger than that range. And you don't want to sell bolts that are going to go onto nuts and be loose. You'll lose your bolt business. Same thing if you make bolts that are too tight to go on the bolts they're supposed to fit. People who are in the construction trades will notice, and your brand will lose its market share quickly to other bolt makers. At least if capitalism works out how they say in economics introductory classes. And when you're in a manufacturing process, if you've been manufacturing these bolts for months or years, you're going to have a great estimate of the standard deviation for the individual bolt's diameters. Here it's 2/100ths of an inch. Whew. So you're making bolts and you want to know, how likely is it, what is the probability that that manufacturing line would be shut down unnecessarily? So if it was working well, but you end up with a sample mean that's either too small to trust what's going on or too big to trust what's going on. Shutting down the line for adjustment might be expensive and cost, person hours and affect your profit from bolt sales that week. And those are things that, bolt makers care about. Heck, if you didn't even care about profits, if you were living in a anarchist communist utopia where you made the bolts just to put things together in a cool way and share them, you still want them to work, and you're still losing person hours when you got to shut things down unnecessarily. You still want to do good work, whether you're doing it for cash or for the love of your fellow human beings, or for both. Okay, complicated question, and the note says, hint, find the probability of finding a sample mean, X bar symbol, in the shutdown range when the true process's mean is a 1/2 inch. Pretty complicated. Let's work through it on the class notes. So all my notes are here. I think I do have a slide with the old, like a pass at this from like 2022 or something, but it's nice to work through it at human speed, and the slide's there for some reference as well. But let's work through this at human speed. I'll just take a picture of the description. Oh, wait, that's a big wordy description. I don't want a picture. I want to copy and paste it. Copy. Sampling, distribution, bolt manufacturing example. Let's put the thing in italics. We've got the whole description right there. Now, let me show you how I approach problems like this. I want to sort out the information they're giving me. I want to use the symbols that I've been using in the slides this whole time, because they just help me recognize which formula is correct and use the right formula. A sample of 36 bolts, no problem. N is sample size. So I'm going to get my N equals 36 bolts right there. I don't lose track of the units in my notes, at least at the first stage. they tell me the standard deviation for, oh, sorry, and the average, both the mean and standard deviation for the population of bolts. So if the process's mean is half an inch, that's Greek letter mu. Should I try to type it out so it looks classier? I could do it. I think I can do it. Where's the math stuff? Insert. You can get all your Greek letters. The fastest way is this equation path if you want them. They just go like that. Mu. Does that work? No. Maybe I don't know how. Oh, there it is. See there, my little Greek letters? Give me. New equation. Give me a Greek letter. Mu is halfway through the alphabet right there. There's mu. Mu is 1/2. That's population mean. Bolt size. Inches, 1/2 inch. And standard deviation, that's sigma. Again, I can use this insert equation as a quick way to get a Greek letter if I want one for my notes. Sigma is also about halfway through the Greek alphabet of lowercase characters. Sigma is 2/100ths of an inch. Population, standard deviation of sizes. For my notes, get those numbers in there. Got the number, I got the population mean, mu, the population standard deviation, sigma. Okay, now what they want is the probability that the manufacturing line will be shut down unnecessarily. That's that, let's say X with a bar is mean bolt size. No? So the population that the mean bolt size is either less than 49/100ths or that it's greater than 51/100ths. Bolts that are either too tight or too loose to work with the nuts for which they're designed to be, to happen. Okay, now, if I had a better stamper for a star for my notes, I'd put a star right here. As soon as we notice that we're talking about probability of finding a sample mean, whether we're using the phrase sample mean X bar or the symbol X bar, when we notice that, that's the moment that we think, okay, this is one of those sampling distribution problems. I'm gonna have a predictable statistic. I just have to do some work to make sure I've got the right mean of those means and the right standard deviation of the means. Looking for probability of a statistic X bar, sample mean, in a range, use the sampling distribution. I'm yelling at myself in my notes, as if I was a learner. Or maybe I won't yell at myself, sorry. But I will emphasize that properly. So a screen reader would say, emphasis, you know. Italics are a good way to emphasize things in your notes. Now, whenever you're going to use a sampling distribution for a statistic, they've always got their own mean and standard deviation. Those were the things back in the notes. So sampling distribution should be normal with mean of the sample's means, and symbolically that's mu subscript X with a bar, so I'll be a good citizen, mu. Subscript. Oh, kidding. And all these little letters and symbols. Hey, look, there's X with a bar. Oh, it didn't do it. X with a bar. It's not a subscript. How do I make a subscript? Like this? Do I type it and then say no? See why I just use underscores for things? Okay. Oh, that's. Oh, that worked. I'm learning as I go. And make my notes look classy for you. Look at that. There's the symbol. U underscore X with a bar. That's the mean of the sample's means. And that's just going to be the population mean, which is just this number. Mean is half. So mean of samples means, population mean, you'll always be given that in this section's homework. Out in the real world of research, you often don't know the number because that's why you have a sample. So, and then standard deviation of the sample's means, symbolically, that's, now I know how to do this, Greek letter sigma, subscript, X with a bar on top. Look at me learning how to type the math like a little champ. That's going to be, there's a little formula. We take the standard deviation of the population and divide it by the square root of the sample size. So I'll type up the little formula in a classy way. I've got population standard deviation sigma, divide that by the square root of sample size, like that. Oops. That's just some numbers. Population standard deviation is 200ths. Divide that by the square root of sample size 36. Hey, that's math I can do. The square root of 36 is 6. 2/6 is 1/3, right? So that's going to be 0. And then that's the 2 I'm dividing by 6 right there. So it goes down to, it's like 1/3 of a percent. That's the result. 1/3 of a percent. Whew, okay, pretty relaxing. Small standard deviation, just like we would expect. Standard deviation is the crucial step. So for my notes, adjusting standard deviation from the population to sampling distribution standard deviation is the crucial step to get this right. All that in italics. Once you're in this world of probabilities about statistics, you've got to get the right standard deviation. There's going to be a formula floating around somewhere in your life. If you don't know where it is, ask your instructor and I will point you in the right direction. Okay, and then now the question we have at the top, the description of the probability we need, we can just draw that out. We have the mean of the varying sample means. We've got the standard deviation of the varying sample means. I can draw that picture for my GeoGebra calculating needs. Slow it down to human speed so I get it right. Get my pen. Red for my bolt factory notes. Because, you know, that's a bad looking. Try to draw a pretty good bell, fairly symmetric. In the center, that's 1/2. That's the population mean. Centers are distribution of varying sample means. Our standard deviation here. So from the center about out to that concavity point, 1/3 of a percent or 0.003333333333. I'll type it like this. 4 decimal, get some accuracy in there. And then we want to know, so if you go out to down to 4900ths or up to 5100ths, you're going to go, well, it's 1/3 of a percent is the standard deviation. So you got to go 3 standard deviations to get out to those values. That's not hard to sketch in my notes. There's 1 standard deviation, there's 2 and 3. And then down here, a 1 and a 2 and a 3 standard deviations. So down at that, down here is 4900ths. Up here is 51 hundredths. And the area I want to find is going to be the area. If they're going to shut down this machine, they got to be all the way out there or all the way up here. So that's my little picture to guide my GeoGebra calculation of this particular probability. Cool. So let's calculate. Let's get the result. It's going to be a really, really low likelihood. That's already good news for the factory people. Great. Your bolt quality control is not going to lead you to shut down too often if you don't need to. But let's find the number as accurately as GeoGebra gives it to us. Again, I'm going to just move my little notes so they're legible to me as I calculate. The mean of the sample means for bolt size should be 1/2 inch. The mean of varying sample means for bolt sizes should be O, and a ton of 3s, as many as I want to type. Hey, look, this is our first example where we're looking for areas below a number and above a number. And GeoGebra does have this cool two-tailed setting for that kind of probability. I can do that directly. X below 49 hundredths. And X above 51 hundredths. And looky there, GeoGebra's picture looks just like mine, but less artistic and more accurate. So I've got a lovely, here's my work. And there's my likelihood. It's real low, 0.0027 after a decimal. Only 0.3% chance of shutting down the process unnecessarily. That's probably good. It's almost never going to happen, although it's not outside the realm of possibility. So for my notes, I've just got calculations for GeoGebra. With my notes, drawn with my notes that guide them. Right here, click. And that's how it looks. The relaxing good times of knowing there's only 0.0027 or about a 0.3% probability shutting down the bolt factory for adjustment while it's working perfectly. Yep. Complicated, but really cool that this kind of theory is actually useful in a genuine setting that is normal. Like people like the products we use to work. I don't want to go buy a pack of ukulele strings where one of the strings is too thick or too thin to sound cool and feel good to play. That would be even worse for me than buying a bolt that was too tight or too loose. Oh yeah, and there's a great question in direct messages. Helping people understand this process, it works best. Get into your homework. Look at the questions in the homework. And then when you've had a shot at them and they look even more confusing, these homework questions from this section are really good class discussion questions, because whether we want to talk about this one-on-one to understand this in detail, which I'd love to do, or we talk as a group to better understand this process and like get more of our hands on how it works, both are good. So one-on-one is great. We can do that during any time we want to get together, or in the classroom is great too as homework questions. This is genuinely complicated. I said that all the way back at the beginning, and this is the most technical statistical section of the whole textbook. So these ideas are genuinely complicated, and just reading the section once or listening to me talk for a couple hours is not enough for most intelligent people to actually understand what we're talking about and how it makes sense. So ask every question, whether one-on-one or here together, and we'll talk about them all. Either setting works for me. And that was the last example, and it's good that I took my notes somewhere else, because I don't have a spring 2022 version on there. Sorry, so yeah, that's with that practice and one example of the complications of the calculations, that should be enough to get you going on the homework and generate those next questions. We'll work through some more examples when the homework questions start to come back to us. Okay. Oh, perfect timing too. We've still got an hour-ish left of class, not quite a whole hour, but enough time to get a start on the next section. And that will get us further into this complicated chapter 4. We'll talk about that more after the break. Right now, rest your mind, let all these complicated details start to percolate in the back of your mind. You do think about things and learn about them even when you're spacing out and looking at the clouds and stuff. So I recommend spacing out and looking at the clouds and stuff. And we'll be back at 17 minutes past the hour. All right, cool.
Yeah, because it's what's the probability that you choose these ones that you're not, I don't get that. Yeah. Because the bigger ones are separate. Okay, and then you can see on that. We estimate the probability that random choice of house was. It's just like a yeah, well, I thought we needed to know that distribution.
Yeah. No.
Is that what the back of it says?
Yeah.
That's what I thought too, and I was like,
Yeah, we should not.
And then the next one says, what's the probability that the mean of 60 randomly chosen houses which are found is more than 1 million? And one game happens to read. Well, Usually the population distribution is not normal, the conditions for inference are reasonably satisfied. What is that? With the possible exception of skew. That if the skew isn't very strong, we should ask to see it. Then, like, what? Then we can use the central limit theorem to estimate this probability. For now, we'll assume that the skew isn't very strong. Then the description suggests it is at least moderate to strong. So what?
So we just say,
And then they use this formula, which what is this formula?
well, that's the SU one.
Maybe if they were like ready to go, they didn't push them in time.
No, I told them to, but I'll set it.
But what's the 0.3? What do they do? But do we know what the standard deviation is?
So they're.
The standard deviation.
It just wasn't showing up, I was just.
You do, what you do is you do this over the square root of 60.
Which would be.
60 root. But they don't do 30,000, they do 0.3.
They bump it over.
What do you mean they bump it over?
Just make it smaller.
But use,
We've done that one. I don't know how much we got about, not sorry.
I don't care how they get to turn it to 0.3. And these go, what's going on in this? Like, what are they doing? Like, I understand that they're putting it into this formula, but they're also
Yeah.
like actually not. Like, I understand the root over 60, but why is this their standard deviation 0.3, not the root 300,000?
That's the one.
Why would it be that? That's, in here, it just says.
Every step.
Oh, I think,
They're just not gonna help them.
well. Oh, okay, I know why, well. I think they're just turning this to be a multiple of millions.
Yeah.
So instead of doing that, you could also turn this into 140000000.
Yeah, that's, they're just.
Okay.
It's more manageable, but I feel like they should.
I'm gonna do that. I'm gonna do,
Oh.
I'm gonna see if it's still 30,000. I'm gonna do 30. Oh, this is. Yeah. Over the square root of 60, right?
Yeah.
Equals, and that tells us what?
That's.
What does that mean?
That's so funny. Wait, he's the guy,
Yeah, yeah.
the guy.
So I go like that.
It's so funny. Wow. Oh my gosh.
So now we have standard deviation, so
Why
what?
would she want to? I know.
What is the Z-score?
It's just so fun. That's, then I was going through it. It's so much.
What, they just put an air button? Also, that's. I got 38,729. What are you doing?
All right, I'm back 1 minute early. I'm feeling great. Look at that. I even looked at my computer and didn't look at it for 2 minutes too long. That was great. All right, team.
ST is a Z-score. One Z-score is one S. But what is this arrow mean? I don't know. Then I look at the record and look, and that's not what I thought.
All right, all right. We are back. We are back. Check this out. We did it. We successfully talked about the second section of chapter 4, the complicated analytical topic of the sampling distribution of a sample mean. Now, you might think, dang, okay, so the first section of this chapter, we got that normal distribution, this lovely smooth curve. We learned some of its traits and how to use a computer to get some calculations done. Okay, that was a level of complication. Now, on the second section of the same chapter, we're telling you that, hey, if you know certain things about the population, like a population mean and standard deviation, you can use that same normal curve to answer more complicated questions about the likelihoods of seeing sample means in various ranges. And that involves that tricky moment of thinking through, you got to adjust the standard deviation into this theory to make that work. So now we're at 2 levels of complication with these probability distributions. The normal one describes bell-shaped distributions in any group. And now we've got this more specific, complicated one, the sampling distribution for a sample mean. Now, if I was the person in charge of the world, if I was the dictator of statistics, I would think that was enough complications for now, and we do something else for a while before we mess with more probability distributions. I'm not, though, the dictator of statistics, at least not yet. Statisticians are such fish swimming in the world of probability distributions that they're like, well, now that they've met those 2, let's give them 2 more. So the next 2 sections of chapter 4, we're going to meet 2 more probability distributions that are for specific probability settings, and we'll introduce more complications into our thinking about that Greek letter mu and that Greek letter sigma and how they really mean different things in different settings. So I'll try to keep the concepts as clear as possible. So hopefully the big picture will make some sense. Although when you look at the weeds here, there's a lot of weeds and there's a lot of details. So whenever you have questions, just ask and we'll do our best to make some sense of these topics together. Chapter 4 really is the most complicated stuff in this course. Once we're past it, things will smooth back out to like more familiar ideas like estimation and developing our understanding of hypothesis testing. But let's go. Let's go to this next section. You'll notice we're skipping the 3rd section of chapter 4. It's got some details about what's called the binomial formula. That's a math formula useful in certain settings. I'll note where it comes up here. You never have to use that formula. We'll always depend on a calculator for any place you would need that. So you don't have to worry about the 3rd section of chapter 4. Unless you're curious about how this binomial distribution works in more detail, you can read it at your leisure and ask me any questions that arise. But we'll start here. Binomial distribution. Anybody know what a binomial is from their math history, their math life? Unless you're like a math major, I doubt you're thinking, oh yeah, binomials. Whenever you took like an algebra class, whether that was high school or in college or both, like some of us did, yeah, well, it's related to a polynomial.
Yeah.
So yeah, it's a two-term math expression. So binomials are things that look like, a great example would be pick an unknown number x and add or subtract any other number. It could be a number you know, like 5, or it could be like an unknown number x plus another unknown number y. You can take the numbers and you could multiply x by itself, that's x squared. You could add it to 27 times y, but as long as there's two things that are products or quotients being added or subtracted from each other, it's a binomial. Just to remind you what the word means, I'll kind of point out why this distribution is called the binomial distribution when it comes up in the discussion. But for us, just remember it's a fancy name, math-based, because of how the math works out in the situation we're going to talk about. Okay, here we go. Let's talk about the situation. Independent yes/no trials. All right. If a random event has only two possible outcomes, I think of them as if you ask a question that's a yes/no question, those are the only answers. So like, did it rain while you were walking to this class from your transportation option on you? Yes or no? There's two options, right? Statisticians label them so-called success and so-called failure. Sometimes those labels make sense and they're useful. Sometimes they're tone deaf at best and problematic at worst. And we'll see examples of both. So, but when you have this yes/no setting and the probability of someone answering yes is the same for everyone you ask the question, and everyone answering the question's answer is independent of everyone else's, that's no one's answer is affecting anyone else's. These are called Bernoulli trials by math people. The Bernoulli brothers were two students of, they were either students of the famed Isaac Newton of Cambridge, the developer of the calculus, or they were students of his students, and they did a lot of important work a couple hundred years ago, developing statistical tools along with a lot of calculus tools. And there's a relationship there because of all these smooth curves in all these areas. Okay, the perfect example of a yes/no trial where the probability is set every time is flipping a coin. If a coin is perfectly fair, you've always got a half chance of flipping heads every coin toss. It doesn't matter how many times you flip tails in a row or heads in a row. The next flip, you've got a 1/2 chance of flipping heads if you've got a fair coin. Yeah? Bernoulli trial is the fancy name for things like coin tosses. Something that's not a Bernoulli trial or is like dealing out cards from a deck to get people hands to play cards. Every card dealt makes it impossible for the next person to get that same card. So there's definitely not independent, and the probability changes as the cards deal out, the deck shrinks, the cards are getting dealt out. You can't have the same probability of being dealt an ace as the person before you at any point ever. So, and there's lots of examples like that in life, things that are dependent or where the probabilities change from trial to trial. Those have nothing to do with this world of binomial distributions. The example that'll drive our sort of descriptive work here, I picked, well, back when professional basketball player of the National Basketball Association, Damian Lillard, was the best player on the Portland Trail Blazers. These are the years between 2011 and I think 2022. He got traded like 2 or 3 years ago, 2023, something like that. But he played here for 11 years. He was the best. And when I made this slide, I think, you know, maybe 2017 or 2018, to date, he had made 88% of his free throw attempts. If you're not a basketball liker of free throws, when a person playing basketball gets a chance to make a shot with no one guarding them from a set distance, and they get a point if they make the shot. Any percentage of success there that's above like 70% is good, above 80% is excellent. The very best free throw shooters in the history of basketball averaged around 90% success. So this is an example where success does make sense. It's truly a success if you make your free throw. Describing not making it as a failure, I don't know. You didn't make a shot, but at least you tried. Yeah. But, and Damian Lillard as a player and a professional basketball player, whether he makes or misses a free throw attempt, that does not impact his approach to the next shot. He's practiced so much that he takes the same routine, he dribbles the ball the same number of times, focuses his eyes, body, and mind on making the shot. Maybe he even visualizes the ball going in. There's all sorts of ways athletes approach a quiet moment of focus and concentration to be successful. One that they all share is you can't be thinking about if you just made or missed the previous shot. You got to put that out of your mind and focus. Much like a pitcher in baseball trying to throw a strike, they just focus on that little box they're trying to throw that ball through. And heck, they focus on the catcher's mitt to try to just hit that target and not think about anything else. That makes that 88% chance, at least back when I had this statistic, a pretty good predictor of his chance of making really any free throw for the next few months or years of his career, at least until he has enough more shots. If he gets better over time, maybe he goes up to 89 or 90%. If he gets worse, maybe he goes down. But for us, his next few free throws, let's say his next few hundred, they're all going to have an 88% chance of success independent of one another. All right, here we go. Okay. Now for the binomial probability distribution, we are always going to be able to use technology for calculations. We're never going to need to use formulas or work through any complicated processes. Though stats teachers as a group, and I think I'm among this group, it can be good when you're using a complicated system to do calculations to at least get a peek at how they work, get a peek at the engine of the calculations. Like if a mechanic works on my car and they open the hood and show me what they've done, I don't understand everything they tell me, but I do get a sense of what they did and why, and it helps me understand that I should pay attention to something if it might need future work or to prevent future problems, right? So when we learn about complicated statistical ideas, we at least have to take a peek at how the calculations get done just to have a sense of the complications. For some people, that peek is really helpful, like for people who are interested in how engines work, talking to the mechanic, they'll have questions and the mechanic can answer them and it'll deepen their understanding of their car. There's people like that in stats classes. And of course, there's also people who are like, dude, I don't want to look at this engine. This is boring. Just be patient with the look at the engine, and then I'll make sure to tell you when we're back to the tools that we're going to use to do these calculations day to day. Like even people who love working on their cars don't look at the engine every time they go for a drive. That would be weird to check it every time. So here we go. Here's the setup. The example is called Make Your Free Throws. Let capital K. A lot of stats books like K in the situation where you've got these independent yes/no trials and a setup like this. Let capital K be the random variable with outcome little k is the number of free throws Lillard makes out of n, like a sample of his attempts, 3 tries. We want to figure out a probability model for the number of free throws Lillard makes out of 3 tries. That's going to list out the possible outcomes. Those are not hard to list, but to also figure out their corresponding probabilities, that's going to be the complicated look at the engine that I'm talking about. It's 3 free throws. When we sort out probability ideas with more than one event in them, a tree diagram is often the best way to sort things out. So I will make one of those in my process. And when we're all done, we'll have an example of a binomial distribution. That's when you know a set probability and a set number of attempts. And you want to be able to give the probability of any number of so-called successes out of that number of attempts. That's the big goal. We're going to make the thing over in the notes so I can type it up at human speed with you, and we'll see how it goes. So it's going to be binomial distribution. Make your free throws exam. I'd say that's a pretty creative name for this section of the notes, and also rather descriptive. Okay, I lied. It's not very creative. I lied. But I like to practice lying for when it's necessary sometimes to not hurt someone's feelings. Okay, here we go. I'm just gonna put some notes here. They said capital K is number of free throws Lillard makes out of 3 attempts. Okay. And what we want a list of the outcomes. So how many shots he makes out of 3 and their corresponding probabilities. Just like back in the random variables section of chapter 3, we can sort it out in terms of happens, what his outcome K would be, and what the probability is for each of those outcomes. Probability little p. And let me make a little more space here. Let's go in the order that numbers happen. If somehow Lillard took his free throws, but for a moment he had like my level of basketball ability. He lost all those years of practice and focus. He might miss all 3, right? Could miss 3 of his shots. That would make his outcome 0. Yeah. Of course, he could make 1 out of 3. Outcome is 1. Probability, I'm not even going to guess at those numbers yet, because it's complicated. There's 3 shots to take. You could make the first one, or the second one, or the third one. My head's spinning a little. I got to draw a tree for probabilities. He could make 2 free throws. No clue on the probability yet. Or he could make all 3. Outcome 3. No clue what that probability is. Okay. I'm looking at this chunk of my page and thinking, can I draw a tree that'll fit there? I think I can. I'm going to make a tree that branches out. First free throw. Oops. Need a better pen than that. Let's go with, he was on the Portland Trail Blazers, whose colors are black and red, back when we made this problem. Let's just go with black. So his first free throw, he could make it. That's like let's call a make like a yes. Oops. I'm going to type. He could make it or miss it. So that's a yes here. Made that free throw. Black, my style here. Or, no, let's not do that. I'll just, or a no right here. His chance of making it is 88%. Remember that success rate? And in a tree, you also want to label the other chance when you can. If you're 88% likely to make something, how likely are you to miss it? 12%. Cool. That's the first shot. Whether he makes it or misses it, he could make or miss his second shot attempt. So that's a yes here. A no there. A yes here. Hey, friend, computer, a yes here, a no there. These are easier to draw on paper than on a computer, obviously. So if you want to draw the branches for the third one, you'll have me beat in your notes. Whether he makes the first 2, he could make or miss the third shot. The pattern just keeps going, more branches. Depending on how you started your drawing, it might be a symmetric tree, or it might look like it's growing in the wind a little bit. And all of the yes paths, I can label them yes. All of the no's get a no. Yeses. I have to kind of get in here and draw the letters separately because my branches are kind of funny shaped. Oh, I kind of broke the pattern there, so I'm gonna change that. See what I did? I kind of was talking and lost track of what I was doing. Oh, I skipped a yes. There's a no, a yes, a no, a yes. Oops. A yes, this one, and the last one, a no. See that? And then I can put that 88%, this little number. Whoops. Every yes gets an 88% on it. Wait, can I do something cool? Can I grab this and go copy and paste? Yeah, that's nice. Then I can just put that 88%. Oh wait, I didn't get the whole thing. Oh, I see. Too skinny. Grab that, copy and paste. Yeah. Yes, there. Paste another one. Yes, there. Paste it. See, I would just be labeling these quickly in my notes with a pencil, but because I'm in the computer world, it's a little more advanced to get all my labels made. 12%, make that a little smaller. Copy it, paste it. I can get the 12% chance of a miss on every branch where it's 12% chance of a miss. No problem. Good old tree diagrams. Really easy to make in your notes by hand. And if you practice being a nerd by being a math teacher for a few years, you can at least make one not that much slower than people who have pencils, labeling every branch with its corresponding probability. Sorry, I said every branch all the way through the graph, right? Starting to look as complicated as an engine. Imagine an engine with lots of tubes and wires going everywhere. Oh, I've got a lot of stuff that's connected by branches, and I got numbers in there, like, spark plugs have numbers on them, I think. I don't know. Maybe. Hold on a sec. Okay, and then as we look through to get the probabilities calculated, it's not that bad if you just look right at the first one. To miss 3, there's only one path through the tree. Missing 3 is bad, so I'm going to make that a red path, okay? If you miss the first shot, no. Second shot, no. Third shot, no. There's your chance of missing all 3. That's the chance of getting 0 makes. And the way the tree diagram works is, what's cool is the probability of no, no, no. You just got to multiply the 12% times 12% times 12%. You just multiply the likelihoods on the branches out, and you get the number that you need. Oh, come on, friend. Hey, come on. Sorry, my computer's being a little bit of a jerk to me. Let me fix this up. Come on. Come on, little computer. Work with Ralph. Make this wider. Make that wider, and I can read my little thing. Okay, looks pretty good. Now, in my work up at the top here, where I'm sorting everything out, I'm actually gonna, for shorthand, repeated multiplication. I'm a math major. I know what's going on. That's just 12 times 12 times 12. That's 3 factors of 12. So 12 to the 3rd power. Sound good, math-wise? Exponents. You might not love them as much as me as a math, but they're great if you want to save paper when you're doing repeated multiplication. Okay. Oh, I typed O instead of 0. Let's fix that. All right. Same idea applies if you well, that was missing 3. We got that one done. Same straightforward idea applies for the best outcome. Let's go green. If you want to make all 3 free throws, this one, there's just one path. Yes, yes, yes. So what's the probability calculation there? Yeah, 88 hundredths times 88 hundredths times 88 hundredths. Or if I don't want to type 88 hundredths 3 times, it's 88 hundredths multiplied by itself 3 times. Wow. There you go. Relaxing. So once those calculations are done, that's mellow. So 88 hundredths to the 3rd power. And I'm not going to get these calculated right now by hand. I'm just going to wait for a minute. We'll check those later. Okay, it gets a little more complicated for making either 1 or 2 free throws. I'm just gonna go in the order they're listed with make one. Because I'm in the green and red world, I'm gonna pick yellow, because that's on stoplights. So to make one shot. Oh, and let me clear out some of the mess over here for my eyeballs right now. Oops. Nope, let me not do that. Let me leave it alone. The mess is good. To make one, you could make the first shot. That's here. Then miss the second too, right? That's one way to make one. Or you could make miss the first shot, make the second and miss the third one. Or you could miss your first two shots and then make only the last one. See that? So there's like three ways you could make either the first shot or the second shot or the third shot. Three ways to make only one free throw out of 3 attempts. We're getting into the math nerd weeds here. If you're following this and thinking, this is kind of cool and interesting, you're like a math nerd. If you're following this and thinking, when is this mechanic going to shut up about this engine? You're like 99% of intelligent human beings on planet Earth. But in any case, any one of those paths, look what I can do. I can just say, top one here, the probability of going yes, no, no, that's just, oh, I erased one of my 88% on my first branch by accident. Let me get that back. Hey, little buddy, it's 88% times 12% times 12%. Good. So that's one factor of 88% for the one make times two factors of 12% for the two misses. And how about a math question from the early days of math learning? No, yes, no is the next way to make one shot. But does the order of multiplication matter? No. 5 times 4 is 20. 4 times 5 is 20. Pick any two numbers, multiply them in either order, you get the same result. Same is true for three numbers. So I don't have to go 12% times 88% times 12%. It's just the same amount, 88% times 12% squared. One make, two misses. And that's also true. That same calculation is also the likelihood of making only the third shot. Same exact likelihood, 88% chance for the one make, and then 12% has two factors there for the two misses. Okay, now we know exponents are shorthand for multiplication. That saved me a lot of typing 88 hundredths and 12 hundredths over and over. What if I don't want to type up this plus this plus this? What's shorthand for repeated addition? Remember that? Math class. Like 6 plus 6 plus 6 plus 6 plus 6 plus 6. That's, how can you do that more quickly? 6 plus 6 plus 6 plus 6 plus 6. 6 sixes. 6. Yeah, multiplication. 6 times 6. Great. We don't usually say what's shorthand for repeated addition. That's the long, nerdy way to say multiplication is the fast way to write this. So over here in my notes for making one shot, I'm just going to go, all right, give me my mouse back. I'm going to go, it's 3 times 88 hundredths for the one make times 2 factors of 12 hundredths, the two misses. So the 3 is the number of paths through the tree, and then the corresponding factors for how many makes and how many misses. And now, without a long speech about the last calculation, can you just tell me what it should be? What's the probability of making 2 free throws here? You could, but I want the number. I want the calculation for a nerdy reason that I will reveal in mere moments. So yeah, once you've got one row left, you can just subtract what you've got from 100%, and you are correct. Though what I want is, I want to see how to do it here. Like we've got, you could either make the first two and miss the last one. You could make the first one, miss the second one, make the last one. Or you could miss the first one and make the second two. See that? Same thinking, but just without me typing along the way. How many paths are there? 3. How many factors of 88% do you need here? 2 makes, 2 factors of 88%. Great. And how many, not 6, I hit the wrong button. And how many factors of 12% do you need? Just 1 for the 1 miss with the 2 makes. See that? Okay. I'm gonna get a screenshot of my big old tree just so it exists in the future. Remember when Elizabeth taught me how to do the keyboard command? That was such a great day. I'm still using the keyboard command weeks later, like a person who kind of learned something. That big. Oh, it's huge. But you can shrink it down a little bit. Be about as big as the drawing was before. Okay, now, you probably didn't want a little talk from Ralph about how fun it was to be a math major. But maybe it's time. Maybe it's time. What do you think math majors do mostly? What's that? Yeah, math. And then there's 2 ways to do it. One is the kind of things we do in elementary school, junior high, high school, and the early part of college math classes like college algebra or calculus or related classes like that have fancier names. But that's like you meet problems and you learn mathematical ways to solve them, whether it's arithmetic in elementary school or algebra in junior high, high school, college, or calculus in high school or college, depending on if you make it to that, if you are interested and go that route. Now, if you become a math major, you do a lot more of that stuff and you learn more complicated methods. And you also learn about why it all works. You learn the theories of mathematics. You have to learn how to prove things work all the time. Whether you're talking about arithmetic, there's a course called number theory. Whether you're talking about algebra, it's called abstract algebra. Or whether you're talking about calculus, that's called analysis. And one of the crucial skills to proving that a math technique always works all the time is pattern recognition. So in the 2 minutes remaining, let me just show you how a true nerd sees the pattern here, and we'll pick this up next class in more detail. The first thing I do as a nerd to recognize patterns is just sort things out in nice ways. Like I'm going to put all my 12% in the same column. See that? Same with the 88%. Like as soon as you search for patterns, you learn to visually set them up. Now, I also know that that's only one factor of 88% there in the make one row, second row. So I could have just labeled that with an exponent, just like all the ones below, right? Same thing's true of this make 2 row, the third row's factor of 12%. Okay. Now, when you're a full math nerd, you learn to love zeros and ones a lot. Like I just revealed a hidden 1 there, 1 factor. In the bottom row, there are 0 factors of 12%. That's exponent 0. Check out that pattern on my 12%. 3, 2, 1, 0. Doesn't get any more relaxing than that unless I go to the other likelihood. Look at this one, 0 factors of 88% right there. And now it's 0, 1, 2, 3. That's counting starting at 0, just like the outcomes. And I've got this lovely, cool pattern for how these calculations work. Now, my probability tree is slightly below the picture right now. But remember the 3 times in the middle 2 rows for making 1 or 2 free throws? It's because there were 3 paths through the tree, right? And look, it's just hanging out here, this part of the pattern. There's only one path that gets me to miss all three free throws. And there's only one path that gets me to make all three free throws. And now look at that. I've got a number that tells me how many paths, 1 or 3, depending on the outcome. And I've got every exponent in there directly related to the number of successes or failures in the setting. And next class, we'll talk much more about this and double check all my work. We can pick it up right here, because I'll just look on our video before class to remember where we left off in this discussion. So get started if you have time, statistical energy, on the work about sampling distributions. If you do some of that work in the next couple days and come back with a question or two, you are going to be a heroic hero to the whole class. Or heck, we'll talk about it next week if that's when we get to it. But yeah, keep coming back with good homework problems. Reminder, chapter 4 is the most challenging stuff this quarter, analytically and math-wise. Every question is good. So just ask them when they arise, and we'll work through them together. All right, great work today with lots of complicated stuff. See you next class. Hey, you're welcome. Hey, you're welcome. Farewell.